Hello and welcome to all to this lecture series on fluid mechanics. This is lecture 1, Introduction and Basic Concepts. So let us begin. First of all, we need to see what is fluid mechanics. Fluid mechanics is a study of fluids at rest or in motion and interaction of fluids with other fluids or solids at the boundaries. Okay, so there are two things in it. One is fluids at rest or in motion and interaction of fluids with other fluids or solids at the boundaries. That is the fluid mechanics. Okay, then we will see what is the behavior of solids and liquids under various forces. See, if there are two plates, okay, this is plate 1, this is plate 2, this is fixed, and this is a movable plate. Okay, and if this movable plate is applied by a force F and there is a solid in between these two plates, and if there is force F is applied, and if A is the area of the plate, then the shear stress developed is given by force by area. Okay, and if this force F is applied in such a manner that elastic limit is not exceeded, then on the removal of force F, original state is restored due to shear stress developed. Okay, so when this force will be removed, the original state will be restored because of the shear stress developed. That is in case of solid. But in case of fluid, it is not like this. In case of fluid, when this is a movable plate, this is a fixed plate, and again there is applied this force F, but now in between these two plates there is fluid, and when this fluid is there, when we apply this force, then these plates continuously move, means the fluids deforms continuously on the application of shear force. This happens in the case of fluid, but in the case of solids, when the elastic limit is not reached or not exceeded, then on the removal of force, original state is restored due to shear stress. Okay, then solids can resist tensile, compressive and shear forces up to a certain limit. And what is that certain limit? It is elastic limit. Okay, and fluids have negligible tensile strength, means fluid cannot resist the tensile strength or tensile force. It can resist the compressive forces only when it is kept in the container. When the fluid is contained in a container, then it can resist the compressive forces. But when it is subjected to shear force, what happens? It deforms continuously as long as the shear force is applied. When it is subjected to shear force, it deforms continuously as long as the shear force is applied. Then there is definition of fluid. From this comes the definition of fluid, that it is a substance that deforms continuously on the application of shear force, no matter how small the shear force may be. Okay, it deforms continuously. There are two important points in this. Please see here, that deforms continuously on the application of shear force. Okay, on the application of shear force, that they deforms continuously. Okay, so a fluid is a substance that cannot sustain shear force when it is at rest. Means when the fluid is at rest, it cannot sustain the shear force. But however, in case of fluid flow, when the fluid flows, there exist shear stresses between the adjacent layers, which result in opposing the movement of one layer over adjacent layer. And this is nothing but the property of viscosity, which we will talk about in the later slides. Okay, this is the property of viscosity, that in that case, when the fluid flows in layer form, like in case of laminar flow, don't get worried about the terms like laminar flow. They will come in later part of this lecture series, but you just take it in that way, that the fluid is flowing in form of layers, and the movement of one layer is restricted or is basically opposed by the adjacent layer. This is due to shear stress. Okay, then there is a term that is known as ideal fluid. What is it? It is an imaginary fluid. Which has zero viscosity, zero surface tension, and is incompressible. Okay, and in reality, no fluid is exist which can be called as an ideal fluid, because all the fluids have some viscosity, some surface tension, and also they are somewhat compressible. Okay, then let us move. Then there are two concepts. One is this concept of continuum and one is this no slip condition. What is this concept of continuum? Concept of continuum means that there are no voids or empty spaces in the distribution of matter. That means that the matter is distributed continuously throughout its domain. It has got no voids or empty spaces. Fluid is considered as a continuum. Why fluid is considered as a continuum? Because even in the case of gases which are the rarest of fluids, because the liquids, which is another kind of fluid, they are more dense than gases, but even in the case of gases, which is the rarest of the fluids, density is very high, and the distance between the successive collision of the molecules is very small. What is this distance between the successive collisions of molecules? This is known as mean free path of the molecules, distance between successive collisions. This is very much less than the system dimensions. Okay, so when this condition is satisfied, that the mean free path of the molecules is very much less than the system dimensions, then the concept of continuum is valid. That means there are no voids or empty spaces, or the matter is distributed continuously throughout its domain. Okay, but however, when the mean free path of the molecule becomes of the order of the system dimension, then this concept loses its validity. That means in the case when the mean free path of the molecules becomes of the order of the system dimension, at that time we say that the system has become rare. Okay, that the system has become rare, the distribution is not continuous, and then this concept of continuum loses its validity, and then we have to go with another theory that is known as a rarefied gas theory. Which is used in the case when the mean free path of the molecules becomes of the order of the system dimensions. Okay, then another major condition which is very much frequently used in fluid mechanics, that is no slip condition. What is it? Fluid in direct contact with the boundary acquires the velocity of the boundary, which means the fluid sticks to the solid and has zero velocity or no slip at the contact point. That means that the fluid sticks to the solid boundary, and when this velocity, zero velocity, is not always there, means that is acquires the velocity of the boundary. If the boundary is a stationary boundary, then the fluid also has zero velocity, and but when the boundary moves with a certain velocity, then the fluid also moves with that velocity, means that fluid acquires the velocity of the boundary, and this property is due to viscosity of the fluid. Okay, this is important, that why this condition occurs, no slip condition. This is due to viscosity of the fluid. Okay, then we have some properties, important properties of fluid. What are those? Let us see. Mass density or specific mass. It is denoted by rho. What is it? It is the ratio of mass. It is the ratio of mass to volume of the fluid element. Rho given by mass per unit volume, and unit is kg per meter cube or gram per centimeter cube. Okay, and when pressure increases, rho increases. When temperature increases, rho decreases. Okay, then another property known as weight density or specific weight, denoted by omega or simply gamma. Okay, it is the ratio of weight to volume of the fluid element, given by weight by volume. Unit is Newton per meter cube. Okay, then specific volume, it is the ratio of weight to mass of the fluid element. Ratio of weight volume to mass means volume by mass. This is reciprocal of mass density or specific mass. Unit is meter cube per kg or centimeter cube per gram. Then we will move on further. Another property known as specific gravity, denoted by SPGR or simply S. What is it? It is the ratio of mass density or weight density of test fluid to the mass or weight density of standard fluid. So given by SPGR or S, rho of test fluid upon rho of standard fluid, and which is also equal to omega of test fluid upon omega of standard fluid. This rho is the mass density, this omega is the weight density. What is test fluid? Test fluid is any fluid whose specific gravity we need to find out. And what is a standard fluid? Standard fluid in case of liquids, it is water at 4 degrees Celsius having the density of 1000 kg per meter cube. And why 4 degrees Celsius? Because water is most dense at this point, that is at 4 degrees Celsius. Lower to it also and higher to it also, water is less dense. It is most dense at this point, 4 degrees Celsius. That is why it is taken as a standard fluid for liquids. For gases, it is air or hydrogen at given pressure and temperature. It is hydrogen or air at given pressure and temperature. Then another property known as viscosity. What is it? It is the property by virtue of which the fluid offers resistance to the movement of one layer of fluid over adjacent layers. This I just now told you in the case of definition of fluids, that the movement of one layer is restricted by adjacent layers. Okay, that is basically the fluid offers resistance. This is the property of viscosity. It is mainly due to cohesion and molecular momentum transfer between the fluid layers. What is cohesion? Cohesion is the force of attraction between substances of two similar kinds, two substances of similar kinds. And what is molecular momentum transfer? When the molecules, the fluid molecules from one layer goes to another layer, there is a change in their momentum, and that is the molecular momentum transfer. And due to these two, that is cohesion and molecular momentum transfer, arises the property of viscosity. Okay, and these effects appears as shear stress, because as I have told you, the fluid cannot resist the shear stresses or shear force at rest. But however, when there is a fluid flow, the shear stresses can be developed, and that appears as property of viscosity. Okay, then in this viscosity, we have a very important law that is known as Newton's law of viscosity. Okay, how it is derived, I am not going into that derivation. That can be looked up in any standard book. This is just a basic simple diagram. These are two plates, one is a stationary plate and one is a movable plate. Okay, and there is basically a line which is horizontal, which is vertical at the initial time, and when there is a force, this force is applied, so this initial vertical line gets deformed or gets diverted into this slant line, or inclined line, inclined by an angle of theta. Okay, so the final derivation, the final relation what we arrive at, that is tau is equal to mu into du by dy, where this mu is the dynamic viscosity and du by dy is the velocity gradient. And mu is known as dynamic viscosity because it involves the component of force. That can be seen from its unit. Its unit is Newton second per meter square. So this is Newton, that is that showed it is a component of force. Okay, and another unit is poise, that is a smaller unit. 1 poise is equal to 0.1 Newton second per meter square. Then another type of viscosity is a kinematic viscosity, that is given by dynamic viscosity by density. It is the ratio of dynamic viscosity to density of the fluid. Its unit is meter square per second, that is a MKS unit, and CGS unit is centimeter square per second, and that is also known as Stokes. Okay, and during the derivation you will arrive at this relation also, that du by dy is equal to d theta by dt. Okay, this implies that velocity gradient, this is velocity gradient du by dy, is equal to deformation rate or shear strain rate. This is your shear strain. Okay, theta is your d theta is your shear strain, and this is d theta by dt is your shear strain rate. So please make a note of it here, that it is not just deformation or shear strain, it is rate of shear strain or the rate of deformation. Okay, then we have the classification of fluids on the basis of relationship between shear stress tau and deformation rate du by dy. Okay, there are broad classification is into two categories. One is Newtonian fluids and another one is non-Newtonian fluids. Sorry, what is it? Newtonian fluid. It obeys the Newton's law of viscosity, that is tau is equal to mu into du by dy. Mu is a function of temperature only. This mu is a dynamic viscosity. What are the examples? Water, air, kerosene, petrol, diesel, all gases, mercury, glycerine, etc. And many more are there. Okay. Non-Newtonian fluids. What are those? They do not obey the Newton's laws of viscosity. Instead, they obey the power law. What is that power law? Tau is equal to tau y plus k du by dy to the power n. What are these terms? K is consistency index, n is flow behavior index, and tau y is yield shear stress. Okay, and this k into du by dy to the power n can be written in this form, and where this k into du by dy to the power n minus 1 is apparent or virtual viscosity. So this k into du by dy whole power n can be written as eta into du by dy, where this is apparent or virtual viscosity. This is non-Newtonian fluids, and this is the power law. Okay, then they are further classified. The non-Newtonian fluids are further classified as time independent, time dependent, and ideal plastic. What are time independent non-Newtonian fluids? In this, the viscosity is independent of time. As they are time independent, so viscosity is independent of time. But however, viscosity is a function of temperature and du by dy. Earlier it was only a function of, here you can see it is only a function of temperature in the case of Newtonian fluid. But in the case of non-Newtonian fluid, it is a function of du by dy also. And it is further classified into two categories. One is known as pseudoplastic or shear thinning, and one is known as dilatant or shear thickening. What is this pseudoplastic or shear thinning? In this, the yield shear stress is 0 and the flow behavior index is less than 1. When du by dy increases, mu decreases. Okay, example is ketchup, milk, blood, polymer solutions, etc. This means that when the velocity gradient increases or the shear increases, the viscosity decreases. When you shake when you have these things kept in a container and when you continuously shake them, so what happens? The viscosity decreases. Okay, these are very common examples. They are ketchup, milk, blood, polymer solutions, and many more. Okay, in the case of dilatant, it is just opposite. When du by dy increases, mu increases. That means when the velocity gradient increases or the shear increases, the viscosity increases. In this case, yield shear stress is 0 and flow behavior index is greater than 1. Example is quicksand and butter solution, and many more. Okay, and then another category, time dependent non-Newtonian fluids. In this case, the viscosity is dependent on time. So viscosity is a function of temperature, du by dy, and one more term, that is time. Another further classification, thixotropic and rheopactic. What is thixotropic? Shear stress, yield shear stress not equal to 0 and n less than 1. And rheopactic, yield shear stress not equal to 0 and greater than 1. That is the flow behavior index. In this case, when time increases, mu decreases. That means when these substances are kept for a longer period of time, they eventually loses their viscosity. Examples, paints, ice cream, yogurt, etc. And when, in this case, rheopactic, when time increases, mu increases, means when the time passes on, their viscosity increases. Example, gypsum paste, bentonite solution, and many more. Okay, and then there is ideal or Bingham plastic. Ideal or Bingham plastic, what is that? In that case, yield shear stress is not equal to 0 and this flow behavior index is equal to 1. So in this case, the power law becomes like this: tau is equal to tau y plus k into du by dy. Examples is toothpaste, drilling muds, etc. So in this case, what happens? The substance or the fluid will not flow readily, but after this tau y or this yield shear stress has been reached, they will start flowing like a Newtonian fluid. In the case of toothpaste, you might have seen while squeezing the toothpaste from the tube, it does not readily comes out. But after, when you increases your after you increases some, you apply some force, and when this yield shear stress has been reached, it starts readily flowing out, and the shear stress becomes directly proportional to the velocity gradient or shear. So that is the example of Bingham or ideal plastic. So you can see in this diagram, this is the relationship between tau, that is shear stress, and the velocity gradient. In this case you can see that this is Newtonian fluid, this is pseudoplastic, this is dilatant, this is Bingham plastic or ideal plastic, this is thixotropic and rheopactic, and this line shows the ideal fluid. This line shows the ideal fluid. Do not confuse this ideal fluid with ideal plastic. This Bingham plastic is an ideal plastic and this is a ideal fluid. So you can see this in this diagram, and this value of tau from this till this point, this is known as the yield shear stress, after which in the case of Bingham plastic it flows readily, and the shear stress is directly proportional to velocity gradient. Okay, then effect of temperature on dynamic and kinematic viscosity. With increase in temperature, fluids, for liquids, mu and nu both, that is the dynamic viscosity and kinematic viscosity, decreases for liquids with increase in temperature, but reverse is the case for gases. While increasing the temperature, this mu and nu increases in case of gases. This is very important relation. They appear in several examinations time and again, so please better make a note of this and also of this. Okay, so this is all for this lecture. Some more properties are remaining that we will cover up in the next lecture. Okay, so thank you for watching this lecture and have a good day.